Let me tell you about a new probabilistic programming language that we built to solve recursive problems exactly. For example, here's a recursive problem. It's based on a trick by von Neumann. Suppose you want to make a decision by flipping a fair coin, and you have a coin, but you're not sure if it's fair. It turns out that you can simulate a fair coin using an unfair coin. Here's how to do it. Flip your unfair coin twice in a row. If it comes up heads-tails, then the result of your simulated fair coin is heads. If it comes up tails-heads, then the result is tails. If it comes up heads-heads or tails-tails, then start over. Here's how you express this trick in our probabilistic programming language. We define a data type flip, which has two elements. We also declare a distribution over flip, called unfair, without specifying yet its probabilities for heads versus tails. We then define fair using unfair. Each of these two lets would perform a flip of the unfair coin, and then the procedure would either start over with this recursive call or end with the result x. Finally, the main program is just the fair distribution. I hope it's intuitive how you could run this program to actually perform von Neumann's procedure, but that's not how we usually use programs written in our language. Instead of actually generating random results, our language analyzes the program and computes the distribution of results exactly. Suppose the unfair distribution is 60-40. Here, our language computes that the fair distribution is indeed 50-50 as desired. This output is exact up to floating point rounding errors. Even better, we can automatically differentiate this fair distribution with respect to the unfair distribution and find that the derivatives are zero. This gives us a hint that the fairness of von Neumann's simulation does not depend on the unfair coin's probabilities. How does our language compute these results? Well, basically the same way you would analyze the probabilities mathematically, by solving a set of simultaneous equations over the probabilities. Our language converts the program into this set of equations. In these equations, we have the unknowns unfair h and unfair t, because the program defines unfair to have two possible values, h and t. Similarly, the equations refer to the unknowns fair h and fair t because the program defines fair to also have two possible values, h and t. These equations can be solved numerically by methods such as Gauss-Jordan elimination or Newton's method. And their derivatives can also be solved easily by Gauss-Jordan elimination. Our language can be used to model and analyze all sorts of recursive probabilistic processes. Here's a slightly less trivial example. You might have seen this puzzle go around on the internet. It's about flipping a fair coin over and over again until a set pattern appears, like heads, tails, heads, in 3 consecutive flips. In one version of the puzzle, the question is, what is the expected number of flips until the pattern appears? It turns out that this expected number of flips depends on the pattern. To analyze this problem, we can write a recursive program that keeps flipping a fair coin until the pattern appears. Every time flip is called, it calls this other thing named tick, and we can compute the exact expected number of times that tick gets called. Internally, this counting feature is implemented by again using automatic differentiation. The puzzle we just solved is related to a paradox called Penny's game. This is a 2-player game, where the first player picks a pattern, like HTH, and the second player picks a different pattern, like HHT. After picking the patterns, the players flip a single fair coin over and over again, and the player whose pattern appears first wins. It turns out, paradoxically, that no matter what pattern the first player picks, the second player can always pick a pattern that is more likely to appear earlier. To study this game, we can write this program, which is composed of 2 recursive functions. The first function generates a list of flips until the first pattern eventually appears. The second function searches this list to see if the second pattern ever appears. The intermediate data structure that serves as the interface between the 2 functions is a list of flips. The final result of this program is false if the first player wins and true if the second player wins. Lo and behold, the second player can always gain the upper hand by choosing the second pattern strategically in response to the first pattern. Now, the way our implementation computes this result is again by turning the program into a set of simultaneous equations. As I mentioned before, every possible value in the program becomes an unknown in the equations. But that's a problem because the list of flips in our program has an infinite number of possible values. Does that mean our implementation has to somehow solve a set of equations over an infinite number of unknowns? The answer is no. Before converting to equations, our implementation first eliminates the recursive type flips. The way it does that is a generalization of the famous defunctionalization transform. Basically, it represents the recursive type flips by where it is constructed in the full program. For instance, instead of constructing a list using the variables x, y, and z here, we store those variables and postpone the work into a so-called apply function, which is invoked where the list would have been deconstructed. Similarly for all the other places where a list was constructed. The result is a program that no longer has a recursive type, and that alternates between generating each new flip and matching against it. So that was an example of defunctionalizing a single recursive data type, so that a program that appears to deal with an infinite number of values can be reasoned about exactly using just a finite number of equations. Another way to eliminate a recursive data type is a sort of inverse to defunctionalization called refunctionalization. With this transform, we represent the recursive type flips not by where it is constructed, but by where it is deconstructed, in the search function. For instance, we represent cons with a new function whose body is the same as the body where a cons is deconstructed. The inputs to this function are the two fields of the cons and the two variables used in the deconstruction. Similarly, we represent nil with another new function whose body is the same as the body where a nil is deconstructed. And because nil has no fields, the inputs to this function are just the two variables used in the deconstruction. Now, instead of constructing flips as a recursive data type, we construct functions. And instead of deconstructing flips as a recursive data type, we call those functions. This transform produces another program that no longer has a recursive type, and it also computes the correct answer for Penny's game. What we just saw is that our program for Penny's game contains a recursive type that can be eliminated using either defunctionalization or refunctionalization. However, a larger program might contain several recursive types, and we might have to defunctionalize some of them and refunctionalize others. For example, the program for a probabilistic pushdown automaton would contain both a string type and a stack type. Because of how they're used in the program, the string type must be defunctionalized, and the stack type must be refunctionalized. And it would take more recursive types to generalize from pushdown automata to, say, embedded pushdown automata. Fortunately, we can plan out which types to defunctionalize and which to refunctionalize by running a greedy graph algorithm that finds a viable plan whenever there is one. In this way, our language can express a wide variety of probabilistic models that are useful for natural language processing and computational biology. Our implementation is the first probabilistic programming system that can compile these models automatically into polynomial-time computations. And because these computations can be automatically differentiated, the parameters of the distribution can be optimized by gradient descent.